Hi, my name is Alex Arrieta. Today, I'll be solving question 5a and 5b from the third problem set in connection to the kinetics chapter. Question 5 comes in two parts, part A and part B, and both regard the half-life of a second-order reaction. Firstly, we'll tackle question 5a, then 5b. The initial information we're given with question 5 reads the following. The decomposition of a hypothetical compound, XY, is second order, in XY, and has a rate constant of 7.02 times 10 to the negative 3 inverse molar per second at a certain temperature. Now let's move on to question 5a. 5a reads the following. What is the half-life, in minutes, for this reaction at an initial concentration of 0.100 molar? So, for the sake of better organization, let's just underline the rate constant, K. And we know it's second order, so let's underline that as well. Now, in order to solve this question, we'll strategically divide our problem-solving steps into 3 steps, with step number 1 being collecting and organizing relevant information, step number 2 inputting our information into relevant formulas, and step number 3 doing our calculations and double-checking our answers. So, our first step here will be to organize all of our data and find the relevant information that will allow us to solve this problem. So, we know that the rate constant, K, is equal to 7.02 times 10 to the negative 3 inverse molar per second. And we know that it's a second order reaction. And we also know that we have an initial concentration of 0.100 molar. These are the values that we're going to use to solve this question. Now, this question is asking us for the half-life, in minutes, of this reaction. And we know that it's second order. Using this, we can go back to our formulas and find this formula for the half-life of second-order reactions. And we can find that the half-life formula for a second-order reaction describes the following, where the half-life of a second-order reaction is equal to 1 divided by the rate constant, K, multiplied by our initial concentration. So now we have our values, our variables, and our formulas. The second step will be to input our values into our given formulas. So we know that the half-life of a second-order reaction is equal to 1 divided by the rate constant, K, multiplied by our initial concentration. And we know that our rate constant, K, is equal to 7.02 times 10 to the negative 3 inverse molar per second. And we know that our initial concentration is 0.100 molar. So now, we have inputted these values, and we are ready to solve for step 3, which is doing the calculations and solving for the half-life. So first, we are going to multiply K times our concentration. So 7.02 times 10 to the negative 3 inverse molar times 0.100 molar is equal to 7.02 times 10 to the power of negative 4, with our units here being in seconds. Now, let's input this back into our formula. Do our calculation of 1 divided by 7.02 times 10 to the negative 4, we get an answer of 1,424.5, or 1.4245 times 10 cubed, with our units here being seconds. Now, since we need this in minutes, then we need to convert this using a conversion factor. We know that 1 minute has 60 seconds, so if we use this conversion factor and we divide 1.4245 times 10 to the power of 3 by 60, we get an answer of 23.7, with our units here in minutes. Therefore, the question for 5a is 23.7 minutes. In this way, by collecting relevant data and identifying the order of a reaction, inputting our data and doing our calculations, we have solved for the half-life of a second-order reaction. Now, let's move on to question 5b. How long will it take, in hours, for the concentration of XY to decrease to 12.5 of its initial concentration when the initial concentration is 0.200 molar? First, let's analyze the new data we've been given. So we have an initial concentration of 0.200 molar, and we are still dealing with second-order reaction. and we are asked how long it'll take, in hours, for the concentration of XY to decrease to 12.5 of its initial concentration. So if we turn 12.5 into a percentage, we know that 12.5% is equal to 0.125. Now if we multiply 0.200 molar times 0.125, we know that the concentration we want to get is 0.0250 molar. This is a value that we're going to use to solve our problem. Now we know from the information given to us that this is a second order reaction, and using that information, we know that we can find the formula for the half-life that integrates both the initial and final concentrations, which describes the following. For second order kinetics, 1 divided by our final concentration is equal to a rate constant, K, multiplied by T, which is time, plus 1 divided by our final concentration. With this in mind, we can go to solve the problem and move on to our second step, which is inputting our values into our given formulas. So 1 divided out over our final concentration is equal to 1 divided by 0.0250 molar, which is equal to a rate constant, 7.02 times 10 to the power of negative 3 inverse molar per second, times T plus 1 over our final concentration of 0.200 molar. So 40.0 molar is equal to a rate constant K of 7.02 times 10 to the power of negative 3 inverse molar per second times T plus 5.00 molar. And if we rearrange for T, we get that T is equal to 40.0 molar minus 5.00 molar divided by our rate constant. Now let's move on to step 3 and finalize this question by moving on to our third step, doing the calculations. If you let this run in your calculator, you'll find that T is equal to 4.9858 times 10 squared, with our unit here being in seconds. However, we need this question and we need this value in hours, so we need to set up a conversion factor here. So as we know that 1 minute is equal to 60 seconds, we'll put it alongside it. And since we also know that 60 minutes are equal to an hour, we'll also put it up there. If we let this run in our calculator and do our conversion, we get an answer of 1.38. And since we did our conversion factors before, we know that this is in hours. So, our final answer for this question is 1.38 hours. In this way, by collecting relevant data and differing between our initial and final concentration, we've identified the order of a reaction and we've solved for the half-life of a second order reaction with initial and final concentration.